and it remains stable. Okay, so that's Runge-Kutta. So let's go back now to the next method. So the next method we're going to talk about is the fully implicit technique. Fully implicit, again, is where we start with a time, and then we're evaluating the derivative, but we're doing the evaluation of the derivative at the end of the time step. So what makes it implicit is that you can see here I'm trying to predict ti at j plus 1, but I'm also evaluating the derivative over here at tj plus 1 and tij plus 1. So we essentially have to write an equation that's dependent on itself, which makes it implicit, and then solve that equation explicitly to implement it in MATLAB, or if you just want to leave it sort of as is, you can implement it in ease as is. So let's look through how to do this. First, we're going to take a step from T1 to T2. Right? And once we have that ironed out, then we can go back and take a step from j to j plus 1. So to start off, I'm just going to write out the equations that we have here, and you just kind of pay attention to the indexing. So we're going to start with t node 1 at time step 2. How do we get there? We're going to start from t node 1 time step 1, and we're going to write out our state equation, which I'm copying from the other page, but I'll just have to substitute in the correct temperatures. So we have, from the other page, we had 2 alpha over delta x squared times t space node 2 minus t space node 1. But now we're trying to make this evaluation at the end of the time step, right? So instead of this being 2, 1, it's going to be 2, 2, and it's going to be 1, 2. So we're making this evaluation at the end of the time step. All right, so then that's plus h bar times perimeter over AC times rho c. And we have t infinity then minus t1 at time node 2. And then plus 2 q dot over AC rho c delta x. And all of that is times our time step, delta t. All right, so that's for node space node 1 to go from time step 1 to time step 2. We can do the same thing for the ith node, and I'll just kind of write that out. It's ti2 is equal to ti1 plus alpha over delta x squared times ti minus 1, I minus 1 at time step 2 plus ti plus 1 at time step 2 minus 2ti at time step 2 plus h bar perimeter over AC rho c times t infinity minus ti times 2, and all of that times delta t. This is 4i is equal to 2 to n minus 1. All right, last, let's just write out real quick the nth. So this is going to be tn2 is equal to tn1 plus 2 alpha over delta x squared times tn minus 1 at the n minus 1th node at time 2 minus tn2 plus h bar perimeter over AC rho c t infinity minus tn2 times our delta t time step. Okay, so this is now an implicit equation, right? You can see there's an implicit relationship. We have the second time step appearing on both sides of the equation. So if we were going to solve this set of equations in MATLAB, of course, we'd have to come up with an explicit solution for each of these temperatures, right? But because we're going to first solve it in ease, we can just leave it as it appears here. So let's look through the solution over in ease. So here we are, we've got the same problem set up. So what I did first here was I copied the solution for the Euler step. Right? This is an explicit solution. And copied this over here, made sure it worked. You can see that on the right-hand side, we're still evaluating at j instead of j plus 1. Okay, so we have that, but then we can use that, copy it again, and then wherever you see j over on the right-hand side, because this is a fully implicit method, we just go through and replace all those things with j plus 1. So that's what we did here. So now you can see the j plus 1 being replaced in there. It is implicit, but ease doesn't really care. So we can go through and solve this. Hopefully it solves. And then you can see how we're stepping forward in time with our 6 nodes. We can look at the temperature solution. So we have temperature as a function of position at different values of time, and you can see as the fin activates, the temperature is moving up, right? This makes sense. Eventually we converge to the steady state solution up here, and it will just sort of stop changing. So in ease, it's pretty straightforward. Now, when it comes to solving the fully implicit equations, we can use matrix inversion. But what we want to do is we want to do matrix inversion for every single time step. So we're taking a step in time, doing matrix inversion for the set of equations in that time, in that specific time step, and then using the result of that to move forward in time. Right, so we end up with this linear set of equations, ax equals b, but it's important to note that this vector A, or sorry, this matrix A, is not a matrix in time and space, right? It's a matrix of n equations and n unknowns in space only for a given time step. So if we look down here at the bottom, you can kind of see that we have, for the j plus 1th step, which is what we're going to be solving for, we're going to be doing the matrix inversion for the j plus 1th step at any point. We have an equation for space node 1, space node 2, and so on, all the way to n. All right, so for a given time step, we have this solution that we have to identify. So if we look down at the equations to solve this, I'm not going to write them all out. I just have them here because there's just too much to write out. But let's start with node 1. Okay, so we're starting with node 1, and we're trying to go from time 1, or j equals 1, time 1, to, let's say, time 2, j plus 1. Okay, and this is for space node 1. So to do that, we have this equation. It's an implicit equation, and you can see on the right-hand side we have the previous temperature, right, for time node 1. This is going to be our initial condition, but then we have appearing j plus 1s here, and we need to figure out how to group together the terms so that we can identify the A matrices, or the A coefficients that go into that matrix. So here's doing that for node 1. So again, we are grouping based on space node for j plus 1. And you can see we end up with everything that's multiplying space node 1 at time j plus 1 is shown here, and we're going to call that matrix A entry 1, 1. Likewise for node 2 here. And then on the right-hand side is everything that's left, right? This is our B coefficient. The maybe confusing part here is that we have, appearing here, we have a temperature. And why are we putting a temperature in the B matrix? Right? B is supposed to be our constants. Well, if you think about it, as we've stepped from time step j to time step j plus 1, we already know, like we've already solved for what this temperature T1J is going to be in the previous, either with our initial condition or in the previous iteration of solving and inverting the matrix. All right, so we already know what that is, so that becomes, to us, that becomes a constant, and this groups with the rest of the stuff over here. Okay, so for this time step j plus 1, we have now coefficients here. We can do the same thing for all the other space coefficients here, noting that we have ai minus 1, right? This is an A matrix constructed for this particular time step with n equations and n unknowns. And then again down here for node n. Okay, so knowing that, we can now go look at our solution in MATLAB. So let's pull that up. So here we are with our transient fin implicit. Same setup as before. Now it turns out for this solution, if you look carefully, you might wonder, okay, why are we just doing this? You can see we're just doing it once and we're not repeating it. Why are we just solving this A matrix once? Well, if you look over here on the right-hand side, nothing here is a function of time. Right? Time itself does not appear in these equations anywhere. And so once you've computed the A matrix is exactly the same from time step to time step for this problem. Now, if we had some boundary condition that was changing with time or something like that, then the A matrix probably would not, you would not be able to do that. But here we can only compute it once, or we only need to compute it once because, well, it's not changing, okay? So then what we do is, when we do want to step in time, we're going in and saying, I'm going to take from my time step from 1 to m minus 1, and then I'm going to compute the sort of j plus 1th of these. So here is our first node b coefficient, and this is now going to change with time. Right? This part is changing with time, and it's changing based on the previous temperature. So we compute the b coefficient down here for every single space node for this time step, do the inversion here, and then we have our temperature solution. Okay, and we're assigning it to say for the j plus 1th step, I'm going to use a vector assignment here, and this is equal to my solution. Okay, so now we just step forward in all of our time, and we can do that and then plot the solution. Actually, one thing I wanted to point out real quick was this plotting capabilities, or video capability. So if you sort of follow this, it's a pretty useful way of looking at these types of transient problems. What it's doing is it's going through for each time step, creating a line plot at that time step here, labeling it, and so on, and then using this function getFrame. So if we get the frame of the plot and keep track of all those things, which it does sort of behind the scenes, you can call this function movie. And so if we do this, let's see, there we go. So let's see if it actually plays. So you can see it's actually now looping through time as it's solving the problem. You can kind of see how the solution starts at the initial condition, and it loops, or it ramps its way up towards the steady state solution as it goes on.